Hello, welcome to my YouTube channel. In this video we are going to be studying fluid mechanics. And we're also going to be looking at all the equations that are used to describe the motion of a free-falling object in a fluid. So let's look at a typical diagram that describes this behavior. So we have an object that falls freely through a fluid. Now this is a fluid. It has a weight W, which is equal to mg. It has three other forces that are acting opposite this weight, and this particular one are described as the buoyant force, the viscous force, and the drag force. And F mu represents the viscous force, Fd represents the drag force, then Bf represents the buoyant force. Now the expression for F mu is giving us 6 pi mu RV, where our mu here is the viscosity of the fluid. R here is the radius of this object, then V here is the speed of this object. Then for the drag, we have this expression here, half times drag coefficients, density of the fluid, the cross-sectional area, and the speed of the object in the fluid. Then finally we have the buoyant force, which is giving us rho GV, where this V here is the volume of the object or the volume of the fluid displaced. Density here is the density of the liquid. G is acceleration due to gravity. Then the final force W here is the weight. Now when you resolve these forces, you realize that this weight minus all this one will give us, because they are all forces, this weight minus all these forces will be equal to the mass times acceleration of the object, which is giving us the mg minus 3 opposing forces must be equal to ma. So depending on what you are given, you can look for, you might be asked to look for one missing parameter, and the other parameters will be given. So sometimes we might be asked to find a particular parameter when we experience terminal velocity. Terminal velocity is the point where all these forces acting on this body, right, are equal, and at that point this object will be moving at a constant speed, right? So let's consider that case where the object will get to a point as it moves down and it will attain terminal velocity, that is, the velocity remains constant. So we have this one equal to 0, so it's no longer ma. So at this point we can make mg the Soviet formula, and that gives us this expression. We can substitute the values here, and that gives us this expression. So we now notice that we have the velocity and the square of the velocity, then we have this other parameter. So in case we are asked to find the velocity, we can rearrange this, but that's at this point it becomes the terminal velocity. At this point we rearrange this formula so that it becomes this. So we'll send this one first, send this one second, then bring this one down to this place, which gives us this. So at this point we can calculate the terminal velocity when these other parameters are known, these other parameters and these other parameters are known. Now let's dive into the drag coefficients of any shape. So we have different shapes here, and these are their drag coefficients. Because it's a constant that must be known, the density of the object of the fluid can be known, the velocities we are asked to look for, the viscosity can be given, the viscosity of the fluid, right, and some of these other parameters can be known. But for the drag coefficient, it depends on the shape of the object. If the object is streamlined body, the drag coefficient, which is CD, C subscript D, is equal to 0.04. If it is half streamlined body, it becomes 0.09. and in this case we assume that this body is moving in this direction. So for this half streamline body which is moving in this direction, the drag coefficient is 0.09, which is higher than that of streamline body. If you look at that of a cube which is moving in this direction, 1.05, angled cube 0.8, the cone moving in this direction 0.5, sphere, half of a sphere, you have this. Then the cylinder moving in this direction, this time around this one is a longer cylinder 0.82, this one is a shorter cylinder 1.15. Okay, so the next thing is to look at the cross-sectional area of different shape. So let's see some of the cross-sectional area of different shape. But the first thing you must know is that to know the cross-sectional area of these shapes, you must first of all find out if when these shapes come in contact with a paper, what shape will they leave on the paper. Like if this one you drop it on a plain paper and it can pass through that plain paper, the shape it will create on the paper is going to be a circle. So the cross-sectional area of a sphere is a circle. If you look at a cylinder and this cylinder goes through a paper, let's say the paper is vertically standing upright, right, and you take the cylinder through it and you look through that paper, the shape that will be formed from the paper is going to be a cylinder, and that's the cross-sectional area. But if this particular cylinder is facing us, instead of this part, circular part is facing, this entire curved part is facing us, then the cross-sectional area, and let's say it's moving towards us, the cross-sectional area of this particular cylinder will be a what? Is rectangle, because it's going to take a rectangular shape. So likewise this one, if this one goes through a paper, the cross-sectional area of this is definitely going to be what? Your guess is as good as my circle. This one will be a square, because these are the only parts that will go through the paper. This one will be a circle, this one will be a semicircle. So these are the different shapes, and these are the cross-sectional area. It's very important we take note of that. So that's that. And this particular final expression here is very important when the sphere or the object is very large. Then let's look at the formula when the object, especially spherical object, is very small. So consider small spherical mass. Now in this case, this will be the formula to use: mg minus f mu minus the buoyant force equal to ma. Now what we are considering is that the drag coefficient is approximately 0 when the spherical mass is small, right? And when we talk about small, we talk about diameter of 1 millimeter, right, and below. So, or probably 0.5 millimeter below. Then you can ignore this particular drag coefficients. So we finally have this. So when terminal velocity is attained, this one will be equal to 0. So we have this expression. We already know what this expression, and these expressions are. So we can fix them in, and we have this. Our buoyant force is the density of the liquid, G, times the volume of the object. This one is still this, and mg. Now our m here, if it is not given, we can replace it with what? The density of the object times the volume of the object, and that gives us this, the density of the object times the volume of the object. If you take this one and this together, leaving this one behind, you have something of this form: this minus this equal to this. And now take note what is common. You can factorize them out, and you have this one here. Now at this point you notice that the volume of the spherical object is 4 pi r cube all over 3. Then you can bring it in, and at this point you can do your cancellation. Pi will take care of pi, 2 will take care of 2, leaving 3. That 3 comes down, you are left with 2 over 9. Then this r will take care of this r, so you now have 2 over 9 g r squared equal to mu vt. So this is the expression we have. So we now have an expression for mu vt. So we can be asked to find the viscosity of the fluid or the terminal velocity of the object. Whichever case this formula holds. So let's look at the first scenario. When we ask to find the viscosity of the fluid, this is what we have. Your Vt will come down. When we ask to find the terminal velocity, we have this, and our viscosity will come down. So that's it. So let's look at another nice scenario, which is that of a raindrop. So for a raindrop, this is the equation that we'll be using. The force, which is more or less the weight dragging it down, the buoyant force, the drag coefficients, right, or the drag force. This time around we are assuming that the viscous force is 0, because the viscosity of air is very, very small. So we assume that this one is equal to 0. So under terminal velocity, this part becomes 0, and in that case we have this expression equal to 0. We can send these two back and substitute the expressions into it, and we have this expression for the buoyant force and the drag coefficients. Now our buoyant force is density of air g times the volume of the raindrop, plus coefficients of drag. The coefficient of drag, we assume that the raindrop is a spherical object, is sphere. Then the density of air, the cross-section area, and the velocity of the raindrop. So we can send this one back to this one, and it becomes this, and replace our m with density times what? The volume. So in this case, we have the density of the raindrop, the g, volume of the raindrop, and this expression we can factorize, and we have this expression. At this point we can make our v squared the survey formula. We'll send everything here down to this part, and that gives us this part. Remember that the volume of this raindrop, which is sphere, is this. So if you do our cancellation, you have this expression. Density of air comes down, CD comes down, 2 goes up, making here 8. Then our G, our R will cancel R squared here. Remember, our cross-sectional area of a spherical object is what? Circle. So that's why we have pi r squared. So at this point we can make V the survey formula, and we have this rearranging. Okay, so V becomes the square root of this entire expression, and our density of raindrop, which is same thing as water, can be written as this expression, and that takes care of everything. So thank you for watching. Please like, share, and subscribe to the YouTube channel, to this YouTube channel. Thank you.